Okay, in the previous class, we have discussed how to sample analog signal. So if we have a analog sinusoidal signal or a continuous time signal, a cos omega t plus phi. So sampling of this signal simply means that we have replaced this t with n into capital T, where n is the integer and t is your sampling time, or in terms of sampling frequency, it is 1 by t. So by replacing the small t with n capital T, you get a discrete signal which was a cos of omega n t plus phi. And from this we have got two relations, that omega in this case becomes omega t, or f is equal to f by fs. So if capital F is the frequency in hertz and you are sampling the signal at a rate fs hertz, you get a discrete signal with the frequency of f by fs. So we have seen that a sampling process was nothing but it is a mapping in which the analog frequencies, they are mapped into the digital frequencies. Okay, and for this mapping to be unique and to avoid aliasing, we have chosen a sampling rate fs greater or equal to twice of f max. Okay, if you choose this sampling rate, there is no aliasing. Okay, it means the discrete signal that you will get after sampling, its frequency will be limited between this band, so it is unique, there is no aliasing component. But if you choose the sampling rate which is less than twice of the maximum frequency, in that case you will get a signal whose frequency in the digital domain will go beyond pi, and as a result, when you reconstruct the signal back to the continuous domain, you may get more than one signal. So there was an ambiguity as to which signal the actual samples they have been obtained from. Okay, so this we have discussed in the last class. Now, and we have taken one example also there, that if you have a frequency of 1 hertz and a 5 hertz signal, if you sample both at 4 hertz, you get the same discrete signal. Okay, that is what is called as aliasing problem. Okay, now when this is for one sinusoid only, single frequency, so in many cases what you have a signal which has multiple frequencies. Maybe it has n frequencies, suppose like this, ai cos of 2 pi fi t plus theta I. So a single, it constitutes of n different sinusoids with different amplitudes, with different frequencies and different phases. So in that case, how you choose the sampling rate? So in that case, again, you have to see that what is the maximum frequency in this entire signal, and your sampling rate must be twice of the maximum frequency. Okay, means if you have three signals, you have a signal which comprises of suppose three frequencies. One is 2 hertz plus 4 hertz plus maybe 8 hertz. So what should be the minimum sampling rate for this signal? Maximum frequency in this is 8 hertz, so it should be greater than or equal to 16 hertz. So 16 hertz is the Nyquist rate. Okay, so because when you see a practical signal, you do not get simply one sine wave. Like suppose if you see a speech signal, so speech signal has different frequencies with different amplitudes and phases. Okay, and it is basically a random signal, you can say, and with time the amplitude and the frequency of the signal that varies. Okay, but if you take maybe So it is a random signal like this maybe. Okay, so but in that case you have to see that what is the maximum possible frequency that is available in the signal. So for speech signal, suppose the maximum frequency can go up to 3 kilohertz. Okay, so it means the sampling rate should be greater than 6 kilohertz. Okay, for voice signals. Similarly, if you say for a biomedical signal, maybe ECG signal, the maximum frequency can go up to suppose 125 hertz. It is a low frequency signal. So the sampling rate must be greater than equal to 250 hertz. Okay, and similarly for any other signal. If you say video signal, it has a bandwidth of 5 megahertz. So accordingly, you can choose a sampling rate beyond 10 megahertz and so on. Okay, so by making sure that your sampling frequency is greater than or equal to twice of the maximum frequency in the signal, what you basically assure that the discrete signal that you get after sampling, its frequency is limited between minus pi to pi. As a result, this is a unique mapping or a one-to-one mapping. So you can easily reconstruct the signal from the sampled signal. Okay. Now there is some problem. Sometimes you encounter a problem when you sample the signal exactly at the Nyquist rate. Okay. Suppose I take a signal, analog signal xt, which has three frequencies, maybe cos of 50 pi t plus say 2 cos of 300 pi t, okay, plus sine of 100 pi t. Okay, so this as unity amplitude, this I have taken 2 as amplitude, this as unity amplitude, and phase in all the cases 0. So what is the frequency here, f1? It is 25 hertz, 2 pi f. The frequency of this is 150 hertz, and the frequency of this f3 is 50 hertz. Okay, so what should be my sampling rate? It should be greater or equal to twice of the maximum, that should be 300 hertz. Okay, now if you sample this signal at 300 hertz, let us suppose in place of cos I take it as a sine function. Okay, this is 2 sine of 300 pi t. Okay, if you sample this signal at Nyquist rate, that is fs is equal to 300 hertz, what will be the discrete signal that you will get? It will be simply cos of 50 upon 300 pi n f by fs, then 2 sine of 300 upon 300 pi n plus sine of 100 by 300 pi n. Okay, you can write it as cos of this will be pi by 6n plus 2 sine of pi n plus sine of pi by 3n. This is what is your sampled signal. Okay, and if you see to this signal sine pi n, it is nothing but zeros. All the samples of this signal will be zeros. And why it is happening? Because you are basically sampling the signal in such a way so that the samples they come at the zero crossing points. Okay, if you sample this at this Nyquist rate, the samples will be exactly at the zero crossing point. So as a result, you completely lose the information about this signal. All are zeros. Okay, it is like this. Suppose I take a sine wave, maybe with a frequency of 1 hertz. Suppose 1 hertz frequency. It means this one cycle, this is 1 second time, this is 0, this is 1, this is 2, and similarly you can have one more cycle, this will be 3. Okay, now what is the Nyquist rate for this is 2 hertz. So 2 hertz sampling rate means your sampling time is 0.5 seconds. If you sample this signal at 0.5 seconds, where you will get samples? 0, then this is 0.5, then 1, 1.5, 2, 2.5, 3. So you are basically sampling the signal at 0 crossing points. So as a result, your output sequence, discrete signal, will be nothing but a sequence of zeros. So in that case, you cannot recover this analog signal back from its discrete samples. Okay, so there is a troublesome, you can say, problem sometimes when you choose the sampling rate equal to the Nyquist rate. Okay, so you can avoid this situation if you shift this in phase. In place of this, if I shift it by some phase, I may get a signal like this, and then I sample it. Now I will get non-zero samples at these points. Okay, so the simple solution to avoid this problem is to choose a sampling rate that is greater than twice of the maximum frequency. Okay, so it is generally not advisable to sample the signal at the Nyquist rate, because there may be some situation where you are getting the samples exactly at the zero crossing points and you totally lost the signal information. Okay, so in order to avoid this situation, we generally choose a sampling rate that is greater than twice of the maximum frequency in the signal. Okay, now how we can reconstruct the signal back from the samples? Okay, reconstruction of analog signal, a continuous time signal, from its samples, because you must have a reconstruction algorithm, otherwise there is no utility of the sampling. So sampling in general is a, what you can say, it is a not non-invertible process. Okay, means you have a continuous time signal, you sample it, you get a discrete signal. So it is always not true that you can recover this continuous time signal from its samples. You can recover only if the sampling rate is greater than twice of the maximum frequency. If it is less than this, you will get aliasing problems that you have already studied what is aliasing. Now we look the sampling in a different way, that is in the frequency domain. Sampling in the frequency domain. You will get a different picture of aliasing. So in order to study the sampling in the frequency domain, we will use the knowledge of Fourier series and Fourier transform, and I hope you are aware about that. You have studied in your signal system course. So let me suppose that you have a continuous signal xt, this is t, xt. When you sample it, you are taking its discrete values after every time t. This is uniform sampling. Okay, so 0, t, 2t, 3t. Okay, So this you can say, I will now this in one more uh, explain the sampling in more sense. How you can get the sampled signal is just like if you multiply this continuous time signal with a impulse train. Okay, suppose st, train of impulses, which is delta t here, then at t it is delta t minus t, then another sample at 2t, another impulse in fact, that is delta t minus 2t, and so on. Similarly on the left side, delta t plus t, delta t plus 2t, and so on. So this is my analog signal. I suppose write it as xat. This is a train of impulses. So if you multiply these two, xat, if you multiply this with st in the continuous domain, you get a signal here, which I say sampled signal x of st. Because when you multiply this continuous signal with the train of impulses, so this impulse will pick up only the sample which is at which it is located. So you're getting first sample at 0, then at t, then 2t, then 3t, and so on. Okay. And after this, see, this is everything is in continuous time. This is not a discrete sequence. So if in case of discrete time sequence, what is difference between this x of st and x of n? This is represented in continuous time. When you say xn, it is a discrete sequence where we have lost the time information. Okay. Now how you can recover this xat from xst? That is a sampled version that we have to see. Okay. So for that, we will apply some knowledge of frequency analysis. Now x of st is multiplication of xat and st. Okay, and this st is nothing but a train of impulses. I can write it as delta t minus nt. Okay, delta t minus nt. So summation of n from minus to plus infinity. So you're getting delta t, then delta 0, then delta t minus capital T, t minus 2t, and so on. Okay, this is the impulse train. This is a very important signal in the study of sampling theorem. Now if you see in the frequency domain, in the time it is the multiplication, in the frequency it becomes convolution. Okay, it means if I plot the spectrum of this is nothing but the spectrum of the original signal convolved with the spectrum of this impulse train or the Fourier transform, and there is a scaling factor of 1 by 2 pi here also. When you multiply and when you convolve in time, you get multiplication in the frequency and there is no scaling factor. But when you multiply in time and there is convolution in the frequency, there is also a scaling factor of 1 by 2 pi if you see the properties of the Fourier transform. So I have to simply find the convolution of the input spectrum with the spectrum of this impulse train. Okay, so how you have to find the spectrum of this impulse train, that we will see first. Okay, let me start from a new page. So what we have taken is that we have taken xst, the sampled version, as xat, the analog signal multiplied with st, impulse train, and in the frequency domain, the Fourier transform of these two signals, they get convolved. Okay, with a scaling factor of 1 by 2 pi. Okay, now you have to find this spectrum of st, which is a impulse train. So this is a impulse train where we have an impulse signal located after every time t 2t, 3t, and so on. So this is basically a periodic sequence. Okay, and how you can find the Fourier transform for a periodic signal. Let me revise it. Fourier transform of a periodic sequence, periodic signal in continuous time. When you study the Fourier series and Fourier transform, we generally say that Fourier series is used for periodic and Fourier transform is used for aperiodic signals. But this is not the case. Fourier transform is in fact a unified tool which can be used for periodic as well as aperiodic signals. Okay, and how you apply Fourier transform to periodic signals is just like this. Suppose you have a periodic signal xt. What we do, we first write its Fourier series. Okay, so we write ak e raised to power j omega naught kt. This is the Fourier series of the signal. And how you get ak? This is 1 by t naught or t, whatever you take, integration over one time period xt multiplied with e raised to power minus j omega naught t dt. So this is the Fourier series, this is the inverse Fourier series. Okay, so if I want to find the Fourier transform of a periodic signal, what I do, I first write its Fourier series. Okay, so it will become a naught constant plus a1 e raised to power j omega naught t plus a2 e raised to power j 2 omega naught t plus so on, and similarly then negative values a minus 1 e raised to power minus j omega naught t and so on. This is the Fourier series. Now we have expressed xt as a linear combination of complex exponentials. So if I use its Fourier transform now x omega, what I will get? It will be simply the Fourier transform of this plus Fourier transform of this plus this, because Fourier transform is a linear transform. It follows linearity property. Now what is the Fourier transform of a naught, a constant? For that I use one more property of Fourier transform, that is called as duality. What duality says, that if xt has a Fourier transform x omega, what will be the Fourier transform of this? It is nothing but 2 pi into x of minus omega. Okay, I hope you understand this. This is small xt in time, capital X omega is in frequency. Now what we have done is that in the frequency domain, the frequency axis is changed to time. What happens? What will be its Fourier transform? You will get the function in time, folded, its folded version, and then multiplied with 2 pi. Okay, this is what is duality. It means, suppose if I take a square wave or a rectangular pulse, if you see its Fourier transform, it is a sinc function. This is xt, this is x of omega. Now what is duality? I convert the signal from frequency to time. The signal is same, I have just changed its time axis. Initially it was omega, this was time here. Now t is replaced with omega. This becomes capital of x omega. And what will be its Fourier transform? You have to first change this signal into frequency and fold it. If you fold it, in case this is symmetric, so you will get the same equation, and then scale it with 2 pi, and this axis will become omega here. Okay, it means if rectangle has a Fourier transform of sinc has a Fourier transform of rectangle. This is what is duality property. Okay, now using the duality property, how can you find the Fourier series of this a naught constant? Okay, so for that I use one more concept here. Your delta t, which is the unit impulse signal, its Fourier transform is 1. Okay, so what will be the Fourier transform of 1? This will be 2 pi into delta omega. isn't it? It means if you have constant signal, how it looks in the frequency domain. You have just one impulse at omega is equal to 0. Of course, it will be minus, but since impulse signal it is symmetric, so delta omega is equal to delta of minus omega. So unity signal at xt is equal to 1, which is 1 for all time minus 2 plus infinity. Its Fourier transform is 2 pi delta omega. If it has a Fourier transform of 2 pi delta omega, what will be the Fourier transform of a naught? It is just multiplied with a naught. So you will get its Fourier transform as 2 pi a naught delta omega. Okay. And similarly for this signal, a1 is a constant. What is the Fourier transform of e raised power j omega naught t? Now you can use the frequency shifting property. Okay. Because see, the Fourier transform of 1 is delta omega. The Fourier transform of a11 is, sorry, this is 2 pi delta omega. The Fourier transform of a1 is 2 pi a1 delta omega. Now what is the Fourier transform of a1 e raised power j omega naught t? If you are multiplying in time with a complex exponential, what happens in the frequency? It gets shifted. So you'll get delta omega minus omega naught. Okay, multiplication in time with a complex exponential is nothing but shifting in the frequency by that frequency. So if you have 2 omega naught t here, it will be shifted by 2 omega naught. It means for this signal, your Fourier transform will be a1 2 pi a1 delta omega minus omega naught, and then so on. This is how you find the Fourier transform of a periodic sequence. Okay, so Fourier transform of a periodic sequence, you can say it is 2 pi is now a constant term in everywhere, and inside the summation you can have ak delta omega minus k omega naught summation over k. This is how we find the Fourier transform of a periodic sequence. Okay, now for this sequence, the impulse train, how you get its Fourier transform? You have a train of impulses st delta t, all are impulses located with a spacing of t. So 0, t, 2t, and so on. Now in order to find its Fourier transform, first I have to find its Fourier series because it is a periodic signal. Okay, and if I express its Fourier series, it will be summation of ak e raised to power j omega naught kt summation from minus to plus infinity. So I have to find first what is the value of ak. Ak is nothing but 1 by t integration over one time period xt e raised to power minus j omega naught t dt. Now if you integrate this signal for one time period, so one time period you can say from this point to this point, maybe minus t by 2 to t by 2. So within this time period, one time period, you have only one impulse signal that is located at t is equal to 0, that is delta t. Okay, so you can simply write it as integration of delta t into e raised to power minus j omega naught t over one time period, and this will become 1. Okay, because when you integrate multiply with delta t, it is only present at t is equal to 0. So you put this t is equal to 0 here, it will become 1. So it is 1 by t. So the Fourier series coefficients for this signal, they are always same. So ak is a constant, that is 1 by t. Okay, now I can write its Fourier series for this signal, and that will become st is equal to 1 by t a naught plus 1 by t e raised to power j omega naught t plus 1 by t e raised to power j 2 omega naught t, and so on. And now if I find its Fourier transform as omega, So 1 by t, the Fourier transform of this is what? It will be 2 pi is constant into delta, or you can take 1 by t as just common factor because it is present everywhere. 1 by t, this will be 1 now. 1 has a Fourier transform 1 by 2, 2 pi delta omega. Then e raised to power j omega naught t, its Fourier transform will be 2 pi into delta omega minus omega naught and so on. Okay, so you can also take this 2 pi outside, it is common factor. So 2 pi by t, you will get delta omega, this is this omega, sorry, plus delta omega minus omega naught plus delta omega minus 2 omega naught and so on. So the Fourier transform of this impulse train is again a impulse train, you can say. Okay, a impulse at omega is equal to 0, then omega minus omega naught, that is at omega naught frequency, then 2 omega naught, then 3 omega naught, but the magnitude or the strength will be 2 pi by t. Okay, so you have one impulse here, then second impulse here at frequency omega naught, then second impulse at frequency of 2 omega naught and so on, with a strength of, and similar in the negative side will also have. Okay, so the Fourier series for this simple train is again a train of impulses in the frequency domain with a spacing of omega naught. Okay, where omega naught is basically nothing but it is 2 pi by t. So t is this time, so omega naught is 2 pi by t, right? Now where we have started this theory like this, that you are multiplying, you have a continuous time signal xat, I have multiplied with the impulse train st. What I have obtained is the sampled signal. Okay, now in the frequency domain, your x s omega was 1 by 2 pi multiplied with convolution of this Fourier transform of this signal, that is x a omega, and convolution of s omega. So this s omega we have obtained for this impulse train. Okay, it is nothing but a train of impulses which are located with a frequency difference of omega naught and 2 omega naught, this will be minus omega naught with a strength of 2 pi by t. Okay, now when you find the convolution of these two signals, what you will get? So first you must know what is the spectrum of this analog signal. Suppose I take, as a general example, I take a spectrum like this, in which this signal has a bandwidth which is limited between minus omega and to omega. It means beyond omega and there is no frequency. Okay, this is the maximum possible frequency in the analog signal. Okay, now if I convolve this signal with this signal, the spectrum this with this spectrum, these are two spectrums, now they have to be convolved. Okay, if you find the convolution of this with this, there's a convolution operator here between these two signals, you are getting the spectrum of output. Okay, and if you find the convolution of this with this, so if you convolve first this signal with this signal, impulse train at omega is equal to 0, so the convolution of a signal with impulse signal is the same signal. Okay, it means you are getting different components now here. The first component that you will get will be the same spectrum, omega n to minus omega n. This is due to the convolution between the original spectrum and this impulse. Okay, and what will be the magnitude? If I in place of s omega you write here 2 pi by t, so 2 pi will get cancelled, you will just get this height as 1 by t. This is one part. The second component, now when you convolve this with this, in fact, see convolution, now it is you have what you say, it's a distributive property, that is A convolution with B plus C, it is nothing but A convolution with B plus A convolution with C. This is what I am using. So I am first convolving this signal with this is the output, then I am convolving this signal with this, you'll get different output, then with the third impulse, and we have to add them together, you will get the combined frequency response of the output signal. So by convolving this frequency response with the impulse at omega is equal to 0, you got this, it is the same. When you convolve this with this, what will happen? So convolution of xt x a omega with this impulse, which is 2 pi by t delta omega minus omega naught, this spectrum will be simply shifted in the frequency by omega naught. So this spectrum will be shifted by omega naught frequency, so you will get here this spectrum like this. Now this frequency is your omega naught, okay, omega naught or omega s, whatever you have chosen. Similarly, when you convolve this spectrum with the third pulse here, you will get the same spectrum shifted in frequency by 2 omega naught. So you will get this spectrum shifted to now 2 omega naught and so on. And similarly in the left side, these impulses will shift this spectrum to the left side. This will be shifted to minus omega naught, okay, on a different, this will be a different graph, not on the same graph. So finally what you have to do, you have to then add all these you can say spectrums together, okay. Now when you add all these spectrums together, what you get, a final spectrum like this, which is the spectrum of this sampled signal, that is x s of omega. So you are getting one spectrum, then you are getting the second spectrum, then third spectrum, and so on. So because of this impulse sampling, you are basically getting the multiple copies of the same spectrum shifted in frequency, okay. So if you sample in time, you get repetition in frequency. And when you will discuss DFT, discrete Fourier transform, where we sample in the frequency, you will see there is a repetition in time. So if you sample a signal in time domain, its frequency response spectrum, it repeats in the frequency domain, okay. And this repeats, so this was omega n, this is minus omega n, and this frequency is your omega naught, okay, where omega naught is 2 pi by t, okay. So this is basically the sampling frequency actually. So it is shifted by the sampling frequency, okay. I am taking omega in case you use f. So this is suppose fn, this will be f naught or fs, the sampling rate. Now this point here, if you see this where this frequency will lie, it will be nothing but omega naught minus omega n, or say just write it as omega s, just to be relate this with the sampling. So this is omega s, and this point here will be what? This will be omega s minus omega n, okay, because see this total is omega s, and if you see this point, this is nothing but it is equal to omega naught. From this to point this and this to this is the same interval, so this is omega n. So if I subtract this from this, what this frequency will be? Omega s minus omega. Now you get, now we take three different situations. In one case, if I take omega s is equal to twice of omega n, that is an Nyquist rate, how this spectrum will look like. If omega s is equal to twice of omega n, it means omega s minus omega n is nothing but omega n. It means this edge of the second spectrum, it will start from here only. So you get the output spectrum like this, okay. This is for the Nyquist rate. If you choose omega s greater than omega n, that is more than the Nyquist rate. In this case, omega s minus, sorry, this is 2 omega n. In this case, omega s minus omega n, this point will be beyond this point. That means there is some gap between these two. Okay, so output spectrum will be like this. Okay, there will be some gap between these two signals. And what will happen if you choose omega s less than twice of omega n? So this point will now come here. Okay, it means when you plot it, you will get a spectrum like this, something like this. Okay, this is what is again the aliasing in the frequency domain. Okay, means from this spectrum, this was my original spectrum. Okay, after multiplying this signal with the impulse train, I got this signal for which I have obtained this spectrum, or this or this. This is at Nyquist rate. This is for a frequency which is greater than the Nyquist frequency, and this is for less than the Nyquist frequency. Now from these two signals, from these two spectrums, I can easily recover this. What I have to simply do is that I have to pass this spectrum through a filter, low pass filter, which will only pass this band. Okay, it means the cutoff frequency should be somehow between omega n and omega s minus omega n. If I use a low pass filter here with a cutoff frequency between these 2 points, I will extract this spectrum from this spectrum, and in that case I can recover my signal back. But if you have here from this spectrum, you cannot recover this spectrum because the spectrums are now overlapped, so you cannot remove it. Okay, so you have no option to recover the signal back from the sampled signal, but in this case, in these two cases, you can easily recover it. Okay, and how you recover that, in if you see in the time, what will happen? Okay, so we have started from a continuous time signal xat. I have multiplied this signal with the impulse train st. I have got a sampled signal. Okay, and I have seen that the spectrum of this, or the Fourier transform of this signal, is nothing but the Fourier transform of this signal shifted in frequency by the sampling rate. Okay, so you have you are getting the replicas of the same spectrum. If you sample in time, you get repetition in the frequency, and this frequency by which it is shifted, it is omega s, and this was omega n minus omega n. So omega n is the maximum frequency present in the signal. Okay, so how to recover this original spectrum from this? I simply use a low pass filter which has some cutoff frequency, and that cutoff frequency should be between these 2 points. Okay, this point was your omega s minus omega n. It means omega c should be between omega n and omega s minus omega n. In that case, I can recover the original spectrum back from the sample signal. Okay, so this signal, if I pass it through a low pass filter which has a frequency response like this, if I write it as h of omega, this will give me the reconstructed signal xrt. Okay, and in now see, in the frequency it is very clear that this will only pass this spectrum. Okay, all these replicas, they will be stopped, or images of this will be stopped by this filter. Okay, now how this basically happens in time, because anyhow you have to get a time domain signal. Okay, now see, when you are passing this signal xt, 3 low pass filter, again in the frequency it is the multiplication. Okay, so this and this they are multiplied, you get only this portion, rest is 0. Then the time it becomes again the convolution. Okay, it means our XRT, the reconstructed signal, is nothing but the convolution of this signal input, that is X of ST, with the impulse response of this filter. Okay, this should be the impulse response of this filter. So first you have to find the impulse response of this filter, okay, which is a low pass filter. So I take this filter, we have taken it. This is the ideal interpolation process. Okay, although it is not practically used, but it gives you mathematical insight how you can reconstruct. So we have ideal interpolation filter with a cutoff frequency omega c to minus omega c, where omega c is in between this, or you also can choose omega c as fs by 2, omega s by 2. This is omega s, so midpoint of this somehow here. This will be half omega s by 2. So generally we choose omega c to be equal to omega s by 2. Okay. Now I'm passing this signal through this low pass filter. Your output will be the convolution between the two. So in order to find the convolution, I have to first find the impulse response of this filter. So impulse response of this filter HT you can use using the inverse Fourier transform. So 1 by 2 pi integration of h omega e raised to power j omega t d omega. This is what is the inverse Fourier transform. Okay, and then you can simply find it. Your integration will be only from minus omega c to omega c. Beyond that it is 0, and h omega is 1 e raised to power j omega t d omega. So you can calculate it. It will become 1 by 2 pi. Integration of this is e raised to power j omega t divided by jt minus omega c to omega c. It will become 1 by 2 pi jt. So you can take the limits e raised to power j omega ct minus e raised to power minus j omega ct. So if I divide this with 2j and here multiply with 2j, this will become a sine function, and this 2j will get cancelled. What you are going to get here is ht as 1 by pi t. Okay, and in the numerator you will get sine of omega ct. This is what is your impulse response of this filter, which is basically in the form of, you can write in the form of sinc function like this, sine of omega ct. So you can write it as 2 pi fct upon pi t is already there. If I multiply with 2 fc and divide with 2 fc, this will become a sinc function. So it is 2 fc into sine of omega ct divided by omega ct. So for this signal you have this impulse response now. Okay, your ht becomes 2 fc multiplied with sine of omega ct upon omega ct. Okay, so if you choose omega c as omega s by 2, so in that case you can further reduce it to 2 fc into sine of omega s by 2t divided by omega s by 2t, or you may also write it as 2 fc into omega s is 2 pi by t. Okay, so if you write here 2 pi, 2 will get cancelled, you will get sine of pi by capital T into t divided by sine of, sorry, divided by pi by t into t. This is what is your impulse response of this filter. Okay, so it is a sinc function basically. If you plot it, you are getting a function like this. Okay, so at t is equal to 0, this sine x by x will become 1. You will get this magnitude as 2fc. And where will be the zero crossing points? See the zero crossing points, this will be 0 when the sine argument is pi. Okay, it means if you have this function sine of pi by t upon pi by t 2fc, this is your h of t. So when your pi by t will be a multiple of pi, at that time you will get 0 because sine pi will be 0, sine 2 pi is 0, sine 3 pi is 0. It means your time at which the zero crossing points occurs, that will be nothing but k times t. Okay, it means this will be t, this will be 2t, this will be 3t, and so on. So the impulse response of this filter is a sinc function which has zero crossing points at t, 2t, that is equivalent to the sampling time. Okay, now what will happen when you pass this signal through this filter in the frequency? Okay, it is very clear, you have the convolution multiplication. In time now you have the convolution. So this x of st, which is a sampled discrete sequence, okay, and this will be convolved with this, these two are going to be convolved. So when you find the convolution of these two signals, again using the linearity property, you will first convolve this with this, plus convolution of this with this, plus convolution of this with this, and this is nothing but the sample value at t is equal to 0. This is sample value of the signal at t is equal to capital T, then 2t, then 3t. Now the convolution with the impulse of this sinc function is the same sinc. The only thing is that it will be multiplied or scaled with its magnitude. Okay, so how you get the ideal interpolation? So you have started from x-at analog signal multiplied with a impulse train, you get a sampled sequence x of st. Now I am passing this through a ideal low pass filter. I am getting the reconstructed sequence. Okay, so this low pass filter, it has a frequency response like this. This is omega s by 2 to minus omega s by 2 cutoff frequency. And input signal, this xst, what is this? This is analog signal. When you multiply with the impulse train, you will get its samples at t, 2t, 3t, and so on. So 0, t, 2t, 3t, and so on. And its impulse response, we have just seen, is a sinc function like this. So this is zero crossing point, it has t, then 2t, and so on. Now when you find the convolution between these two signals, that is how you are getting the output. Okay, and when you plot this output, what you will get, you have to first find the convolution of this with the first pulse, then convolution of this with the second pulse, and then add them together. Now when you find the convolution of this with the first pulse, what you will get, you will get the same impulse, same sinc function, because convolution with delta t is the same signal. The only thing is that it will be amplitude, some magnitude will be scaled by the sample value at t is equal to 0. Okay, so we are getting one sinc function. Okay, where this is multiplied with x of 0, the sample at 0. Then when you find convolution of this sinc pulse with the next pulse or impulse, which is located as t naught, so you're getting the same shifted in time by t and multiplied with its magnitude, that will be x of 1 here. This is x of 2, x at 0, and so on. So you scale this magnitude, you multiply it with x of 1, it may be any value 2, 1, whatever it is, and then you shift it in time by capital T, you are getting a second sync pulse. So this is time t. It means you are getting a second pulse like this. Okay. Now the magnitude of this will be different than this. Similarly, when you convolve this with this pulse, it will be shifted by 2t. Okay. So you will get another sync pulse which is centered at this point. Okay. So you will get like this. And so on. You will get infinite number of sync pulses. In fact, the same sync pulse is scaled by the sample value at that particular time and is shifted in time by t, then 2t, then 3t. And when you add all these sync pulses together, similarly you will get a sync pulse here also in the left side. It will be centered at this point. So you will have like this. Okay. So when you combine all these pulses together, what you get at the output is nothing but the original analog signal. So you will get a signal like this, maybe at the output. This is the original signal. So reconstructed signal will be in this. This is XRT, which will be same as XAT. So this is how you reconstruct the signal from its samples. And if you have satisfied the criteria fs greater than twice of x max, so you can assure that there is only one signal that will be recovered. You are not getting the aliasing components in this case. Okay. So this is how you can. This is what is basically interpolation filter. This is called as interpolation filters. Okay. So this is the ideal filter, mathematical concept behind this. This is not a practical, what you can say, digital to analog converter. We have circuits, analog circuits for that we might have studied earlier also. So if you see the A to D converters, sorry, D to A converters, how they work like this. Suppose this is analog signal and you sample it like this. Now from the samples, how you can reconstruct the original signal, there are many ways. One is just a zero order hold circuit. So it samples this point, suppose, and hold it till you get the next sample. Okay, then it will stay here at this point. At this point it will sample it, then it will remain at this level till you get the next sample, then at this level till you get the next sample. So you can from zero you start, you get like this is the reconstructed signal, but this is not exactly what you get it is. Okay. Or another way is you use a linear interpolation. So in the linear interpolation you simply connect that point samples by linearly like this. Okay. This is the output of the linear interpolator. But if you use higher order interpolators, okay, so you can exactly get this signal back from this sample. This is how it is basically done by your D to A converter, the practical D to A converters. Okay, but this was just a mathematical background how you can reconstruct the signal from its samples and how you should choose the sampling time. Okay.